Hi, we are Team 7, and in this video, we will showcase our optimization implementations and testing conducted for the Android app and Flask server. This is our workload model. We are expecting 3,200 requests per day from Android to Flask, assuming that there are 2 SDA officers on site from 9 to 6 p.m., and the request will only be sent when the beacon's RSSI is more than negative 90 dBm. For hops to Flask, we are expecting 17,280 requests per day, with 2 requests sent every 10 seconds. And according to our research, the SDA's records can be stored in a database for 25 days. Therefore, we expect our database peak storage to have 80,000 records. This is our updated system architecture. Everything including the database resides in a Docker container for easy deployment. We have Nginx in front of UWSGI and Flask, where we implemented G-Event and Socket.io. More details will be elaborated later under the Flask server portion. We scaled down our test environment by 50% because we were only testing with 1 Android phone and 3 beacons. After scaling down, the test environment deploys 150 G-Event async cores and 50 MongoDB max connection pool size, and the dashboard will not be polling at all.
Before starting on Android optimization part, one of the requirements was to implement login for the SDA. As required, SDA should be able to improve their staff IP and IP address in order to start using the application, and this code can be found in the login activity.java. We have made use of 4 approaches to optimize our Android Moco Beacon app, which consists of 1. The change in RSSI strength being greater or equal to negative 90 dBm. 2. Configuration for the beacons. 3. Performing sorted binary search algorithm. And lastly, implementing thread pooling. For the general flow of the application, the SDA will log in with staff ID and IP address. Beacons that has more than or equal to negative 90 dBm will be checked first, then undergo a sorted binary search algorithm before creating a thread to send a post request. The reason why beacon RSSI strength was further changed to check whether it has more than or equal to negative 90 dBm is because the team found out that the best detected RSSI value will be best set at more than or equal to negative 90 dBm when we were conducting an on-site test in the campus, simulating the SDA performing their job. During the on-site testing, we discovered that most of the detected beacons near an SDA officer fall within the range of negative 80 dBm to negative 90 dBm. Sorted binary search was implemented to prevent duplicated beacon MAC addresses being sent over to the Flask server constantly and flooding the database when performing insert query. The code was written to compare strings and filter out similar string within an array and return the filtered string back to the function as shown in the screenshot. Other than filtering the duplicated requests and to prevent flooding in the database, the beacon information will only be sent to the Flask server every 2 minutes. The reason why the team opted for 2 minutes delay is so that the SDA has enough time to go over and approach people who have violated the COVID-19 restriction rules. Next, we implemented Threadpool to allow post requests to be sent in parallel and also to optimize the response time and throughput of the post request between Flask server and Android phone. How the thread pooling works in our code is that every time a task is created to send a post request, the thread pool which is used to create threads will spawn new threads for that. As inferred from the screenshot, Threadpool Manager is created to be a singleton class. It creates instance of task queue for the Threadpool executor to send requests to the Flask server. Also, the core pool size was set to 2 to allow 2 threads to be available so that parallel requests can happen. Another reason why the core pool size was not set to a larger number is to refrain from lowering memory usage. We have also added a task class. This task class is created and added to Threadpool executor every time after a beacon with a RSSI strength of greater and equal to negative 90 dBm is detected, and after beacon array list went through the sorted binary search algorithm. The main purpose of this function is to send a post request to the Flask server using the OKHTTP3 API. As shown in the screenshot, the task constructor was added to allow the task creation where it helps to pass the relevant details into the download file where post requests will be sending. For load testing on the response time between Flask server and Android, we use Jmeter to run tests for 10 minutes while 2 post requests will be sent over every 2 minutes. Before optimization, we did not use any multi-threading method while sending a post request to the server. In assignment 2, we added a thread pool and spawn new thread whenever a task is created in order to send a post request over to the server. As can be observed in the result, the average response time between before and after optimization has decreased by 5 milliseconds. We therefore conclude that having a thread pool helped in optimizing response time between Android and Flask server, as it allows requests to be sent in parallel and have readily available thread running, hence increasing the overall performance. As for load testing on the throughput between Flask server and Android, we have also used Jmeter to run the test for 10 minutes, while 2 post requests will be sent over every 2 minutes. This test aims to see if there is any difference in throughput.
Go to the View Results tree, and you can observe a list of successful post requests being sent to the Flask server. So in the Request tab, we are able to see the Flask server URL that we are posting our post request to. After 2 minutes, new batches of requests is sent to the Flask server. This is derived through the timestamp difference in minute between the current batches of post requests and the previous batches of successful post requests. These tests will run continuously for 10 minutes.
The Flask optimization consists of Socket.io, MongoDB, Gevent, UWSGI, and Nginx. Firstly, we chose to use Socket.io to send updates to the dashboard because it provides low latency communication between the client and server. As compared to Ajax, which needs to go through a HTTP server thread to process requests, Socket.io requires less resources and is more suited for this use case. Secondly, we switched over from MySQL to MongoDB because it is suitable for high volume data storage. It supports query optimization by indexing, which is used to locate records more efficiently. These are the indexes that we created to optimize our query. MongoDB also has a max connection pool size that determines the maximum number of connections in a connection pool, which refers to the number of queries that it is able to run in parallel. We experimented with different sizes before deciding that the value of 100 was optimal for our application. Thirdly, our main optimization technique is choosing to use Gevent over threading. Gevent is a coroutine-based Python networking library that uses greenlets. Gevent replaces threading with greenlet-based green threads, making all the code run in a single thread. Greenlets are lightweight using cooperative multitasking. To run multiple requests concurrently, if a call to a function may lead to a blocking I/O operation, Gevent will switch the context to another greenlet. Once the data is ready to be read, Gevent will switch back to the suspended greenlet. As the mobile is sending requests in parallel via a thread pool, this helps us to easily scale up the limit of concurrent requests for our application. We don't need a dedicated thread per request as threads can be expensive in terms of virtual memory and kernel overhead. Instead, each request handling now happens in a greenlet. We experimented with different values and decided that 300 Gevent async calls is sufficient before we might start adding unnecessary overheads to our server. Now we will show you how we implemented Gevent. In run.py, we had to use this monkey patch to make the underlying I/O happen asynchronously, where the socket can operate in non-blocking async mode. Apart from using Gevent to handle the request, we also used it to concurrently update the dashboard and insert the beacon information into the database in our insert beacon function in run.py. This is done so by using Gevent to create new greenlets for each process and schedule it to run using this gevent.spawn function. This ensures that they can be completed asynchronously and a faster response can be sent back to Android. We opted to use UWSGI to enable the use of the Gevent loop engine. We use UWSGI to specify how many Gevent async calls we want to spawn, and we also disabled logging in UWSGI to increase throughput. Lastly, Nginx is used to free the burden of HTTP traffic and performs reverse proxy and passes requests on to UWSGI. Now we will demonstrate the testing of the Flask server using Jmeter. Because we want to test our heaviest workload of having 80,000 records in the database as explained in our workload model, we will test extracting records from a dummy record collection we created. Through testing, we realized that the link speed of the Wi-Fi will affect the results greatly. So the results that we're going to present is using a link speed with over 500 megabits per second. For the response time results from Hogs to Flask, in our slides we made a comparison to our assignment 1 architecture, which had an average response time of 64 milliseconds, to our current architecture where we changed our database, we had an average response time of 110 milliseconds. We realized that it was very slow, so we decided to optimize it further by creating indexes on our database, which helped to improve the performance to have an average response time of 17 milliseconds. For throughput between Hogs to Flask, in our slides we made a comparison to before we optimized our current architecture, where it could send 1,475 requests per minute. But after our first optimization, which is to implement a max connection pool size of 100, it decreased to 1,078 requests per minute. We realized that this is probably due to not having indexes on our timestamp column, which made the query very long. Therefore, after creating an index and testing it again, the throughput increased to 6,239 requests per minute.